Sorry, yeah, thanks for coming to the last seminar of this semester, but the start of the exciting week, right? The end this week is going to be lots of activities, lots of seminars, and specific research meetings and sample parties. And so it's my pleasure to introduce Dr. Su, coming from our brother university, Duluth, and he was reading down there yesterday, and luckily right before snow.
Yeah.
So it's good to have him here, and I was very surprised that his background, before I actually invited him, I was really surprised that his background matched so well with what the SAFO has been doing. And you got his undergrad from University of Science and Technology of China, actually the same school where Lian and I got my undergrad from. And then you did your PhD with Kenny Brewer at Brown University. I don't know how many of you remember, Kenny was here several years ago. Unfortunately, I didn't get a chance to meet Kenny and because of personal travels, but I always feel my research is well connected to your group. Kenny is a very influential person in the experiment of fluid mechanics, has done work ranging from microfluidics to larger scale biolocomotion. I think they have the only wind tunnels that study bats.
Live bats, bat flying,
bats in the building. And he said done very fundamental work on the turbulence and the microfluidics, but also translate that work to building innovative robots, like bio-inspired robots with specially designed wing shapes and etc. So as a member of that team, I guess you carry a lot of genes of that lab. So you can see his work has been very diverse, coming from the energy harvesting to environmental to some biological stuff. All right, with no further ado, the floor is yours.
Thank you. Thank you. Thank you for the introduction. It's nice to be here, even though it's kind of like a snowing day. But luckily, I got here yesterday afternoon before the storm. I was expecting some like a warmer weather, but actually no. But actually, it's warmer than yesterday. This is great. Today, I will be talking about various topics about this energy harvesting and this aquatic animal locomotion and some related fluid mixing. So to start with, I would like to start with the ocean. The ocean is large. It covers more than 70% of the Earth's surface, holding vast energy resources, including those wave energy, flow energy, and thermal gradient energy. And this can present a great potential for the sustainable solutions. And also, ocean is home to many highly efficient biological systems. For example, there's various fish, jellyfish, krill, which have evolved over millions of years in those underwater, complicated underwater environment. And thus can also offer those engineering innovations. But despite those potentials and innovations, so the ocean energy is still underutilized due to many technological challenges, for example, those harsh conditions, difficulties in maintenance, etc. And also our understanding of this ecosystem is also limited, and thus as for an urgent need to advance those technologies and innovations to help us explore this underwater environment. The good news is that it's running. The good news is that those environment or the nature has solved many of those challenges for us. For example, those marine animals, jellyfish, and the krill, which have evolved highly efficient way to move, and then we can use the strategies to inspire the design of bio-inspired robots and those energy harvesting systems. And those energy harvesting systems can also be miniaturized and then integrate into those bio-inspired robots to enable those long-term self-powered autonomous ocean missions, that's also reduce the reliance on those external power sources and extend its operational capabilities. And the key aspects between those marine animals and the energy harvesting is the fluid structure interaction, as you can see here. And understanding this interaction is also crucial to maximize its efficiency and adaptability in those underwater settings. And to explore those challenges and opportunities, I identified 3 questions in my research. The first one is, how can we optimize this energy extraction from the ocean flows in various forms? Second is, what can we learn from this biological locomotion? And the third is, how can we bridge this energy extraction and biological propulsion? So it is large topics, and then I don't think I can cover all of them. But in today's talk, I will be talking about mainly 2 parts. The first one is about ocean renewable energy harvesting, with examples in the tandem foil energy harvesting. And then I will introduce a subphysical system, and I use 2 examples, a short example about energy harvesting, and the other one is about flow-induced vibrations. And then I will talk about those marine animal locomotion, talking about those cobra swimming, those jellyfish swimming, etc. Then I will wrap up. So ocean energy harvesting. So the energy is essential to modern society. However, most of those primary energy sources are unsustainable. As you can see in this chart, more than 74% is from fossil fuels, while only 21% is from those renewable sources. And those reliance on those fossil fuels can contribute to those greenhouse gas emission, and then potentially cause the rise of global temperature and the climate change. And then transitioning to those renewable energy sources is crucial to mitigate those environmental impacts. And among those, the ocean energy is abundant and largely untapped. So for example, this ocean wave energy can be harnessed using those, for example, those up and down motion of the buoys. And also the ocean flow energy can be captured using those rotary turbines, which are very similar to the wind turbines here, as you can see here. And also those flapping foils. Despite its potential, so the ocean energy research and the technologies are far from being fully developed. And in this talk, we'll be focusing on those ocean flow energy harvesting using the flapping foils, as the flapping foils presents unique advantages in the underwater settings. The first thing is that the tip speed is low compared to those rotary turbines, as you can see here, and therefore it is quieter and safer to those marine animals. Second one is the wake of those flapping foils is structured with vortices, and these vortices can then be recaptured by the nearby or downstream foils to enhance or boost their performance, which we'll be talking about later. And the third one is that those flapping foils are more scalable in this horizontal direction. As you can see here, they're horizontal, which is more ideal for those shallow water deployment. Just imagine that you're running this system in a river or in these coastal areas. Okay, so here's the experimental setup we use to do the experiment. So basically, the flapping foil consists of a heaving motion, which is a linear motion, and a pitching motion, which is a rotating motion. And there's a 90-degree phase offset between these two. So you can see in this video here. And this is combined. The flow is from left to right, and then you can see this going back and forth to extract the flow. So usually we use sinusoidal wave form, and the parameters include the frequency, hip amplitude, and the pitch amplitude here. And those are from this literature, and basically this is the range is about, well, the range, dimensional range is about that, but you have the non-dimensional range later we'll talk about. This is a sketch of those 5 different locations of the foil so that you can see the angle of attack with respect to the flow angle here. We also have a force transducer on the top to measure the force, and this force including the lift force, which is in the heave direction, and the pitch force, the torque in the pitch direction. And together we can use this measured force to calculate or assess this extracted power using this equation. And then we can normalize the power using the total available power in the incoming flow, which is roughly defined by here, the energy in this window, flow window width here. And one take-home message is that in this flapping foil, the heave component, which is the translating one, is the dominating component compared to the pitch one. And another take-home message is that optimal reduced frequency range is about 0.1 to 0.4, and the reduced frequency defined as the motion frequency, the chord length over the free string velocity. And we'll come back to this reduced frequency a little bit. So the first project I would like to talk into detail is about the tandem foil energy harvesting. So this project was finished at Brown University with Professor Kenny Breuer. So there is a lot of literature on those single foil energy harvesting using these flapping foils. And as I just showed, there's the parameter, the optimal parameter, frequency, heave, and pitch amplitudes. And then eventually you want to deploy multiple devices. And then the simple question is, what if you want to deploy two energy harvesters, and the one in the upstream, one in downstream, and then the question is, where do you place the downstream foil in order to get the maximum energy output? And let's just consider a simple scenario, which is one right behind the other tandem foil. And to understand, address this question, we look at the literature. This tandem foil interaction has been studied in various different areas. For example, there's simulation here, numeric simulation, and then there's insect wings, tandem wings in this dragonfly, and also fish fins, etc. Also, researchers identify a few important variables or parameters, such as this phase between those two foils and frequency, etc. But the question is that those explored parameters are isolated or limited, and that is to say those identified optimal parameters in one case might not work for other cases with different configurations, with different sizes, with different spacing, with different parameters. Basically, it's only true for that specific explored case. There's no unified theory that can describe those tandem foil interactions, especially the performance of the trailing foil. So to find this, we did some lab experiments. So we have two foils in the flume. One is upstream, one downstream. I have two force transducers to measure the force. And then we prescribe those two foils to have the same kinematics, the same heave, pitch, amplitude, the same frequency. And the only different thing is there's a phase in between. There's a phase psi here. Basically, so if the psi is 0, that means two foils are running the same way. If it's 180 degrees, running this way, back and forth this way, if the flow is on the other direction. And then, so the phase is an important parameter here. And we set the heave amplitude, pitch amplitude the same for both. And we then estimate those energy harvesting performance for both foils using the same equation here. Also, we visualize the flow using PIV experiments to better understand what is going on there. So yeah, let's look at the results. So we have two foils. This sketch, we fixed the separation between this foil of to be 6 cores, uniform flow, and then we verify those. We change the phase in between them. We basically sweep through all the phases from minus pi to pi, or from minus 180 degrees to 180 degrees. And for each dot here is just one, we run the system at one specific phase, and then we estimate the efficiency here. So for example, here we explore 4 different reduced frequencies here. And for each reduced frequency, we have a curve for the leading foil and a curve for the trailing foil, and the performance at different phases. And first thing we can see that the efficiency for the leading foil does not change with respect to the interfoil phase, which is reasonable because the leading foil is 6 cores upstream of the trailing. The disturbance cannot travel upstream with considering those flow velocity. But we can see that the trailing foil efficiency, there is a lot with respect to the interfoil phase side as well as the frequency. You can see the red curve, it has the maximum around minus pi over 2. For the cyan curve, the maximum is around maybe minus pi over pi. So this dependence might be really a big problem if you want to design such a tandem foil energy harvester, because you don't know where to put the second foil in order to get the maximum energy out without testing it, without build and testing it, right? You have to test it. Okay, yeah, this is the maximum position and maximum energy at this specific position. So without knowing this beforehand, you cannot design this. And then, so let's try to understand this data. So because the wake from the leading foil will be traveling downstream and affect the trailing flow. So we first look at the convection time. The wake travels from leading to the trailing, which is given by the separation divided by the convection velocity, speed here. And then we can estimate this convection phase, which is with respect to 2 pi ft. And then we can reorganize the convection phase with respect to the reduced frequency here and the dimensionless separation. Here we define a velocity ratio, which is the convection velocity over the free stream velocity. So now in this final form, the convection phase in terms of the reduced frequency, non-dimensional, dimensionless separation, the velocity ratios are all dimensionless. It's not depending on any size, foil size, or the distance. And then we combine this phase because the effect is both the convection phase and the interfoil phase over here. And now we use the global phase, which is the sum of those convection phase and the interfoil phase. Now we then replot the efficiency with this, with respect to this global phase. We can see that all those curves now aligned with those minimum efficiency are at a 0 global phase and maximum at minus pi or pi. This sense is working. But this is also validated at one case. That means it's one separation and then one flow speed. What about other conditions? Yep.
Just want to get some clarification on the Reynolds number regime where the energy harvester is
Yep.
located. I don't know whether you have the Reynolds number somewhere.
Mm-hmm.
Is there a region for this periodic bubble shedding?
Yes. Yeah, the good question. Yeah, the Reynolds number region is about 50K, 50,000. It is with this energy, this vortex shedding region. Yeah, there's a large vortex shedding with this specific frequency, amplitude, and heave amplitude and pitch amplitude. Yeah, you will be seeing those in the PIV measurements in later slides.
So you design the core length.
The core length. Yes, exactly.
Incoming flow speed.
Mm-hmm.
Set your Reynolds number within the region.
Yeah, yeah, mm-hmm. Yeah. And so, for example, like in this case, if it's like 0.53 meters per second, the Reynolds number will be about 50,000. Yeah. Mm-hmm. So, yep, to validate this model, and then we repeat the experiment, different flow speeds as well as for different separations. Here, different speeds and different separation. We can see that others curves collapse, and suggesting that this global phase model works to collapse those curves as well for those separation as well. You can see then from 6 to 9, it was really well. You can predict those, basically you can predict the location of the optimal energy harvesting. Yeah, and then in this case, when you want to design a tandem foil energy harvester, you just need to plug in your parameters. For example, you want the spacing to be 9 or 6 cores, and then you want your frequency, reduced frequency to be 0.1 or 0.11, which is the optimal range. And then you just need to plug in your number here in this global phase model, and then it will give you a corresponding interfoil phase. And with this phase, you will get the optimal energy output for the trailing foil. And then to further look at those things, what is going on, and so this is the PIB setup. We did some flow visualization. So this is the regime. This is a sample video showing the large leading edge vortex shedding in the flow. And so we look at both the leading and the trailing foil here, and then we look at two cases. One is the optimal case, high efficiency. The other one is low efficiency. Instead of looking at the vortices, we look at the flow angle. I think it's more straightforward to show what is going on here in the flow. So the flow angle is defined as the velocity vector is pointing up and is positive. If it's pointing down, it's negative. So with this definition, we have this contour map here in this velocity field. And then for those optimal case, we can see that, let's just only look at the trailing foil. You can see that when the trailing foil is going down, that the vector is pointing down as well, which will increase the angle of attack. When it's going up, in the same way, the angle of attack that the trailing foil sees will always be increased or enhanced by the incoming flow, as you can see over here. And on the other hand, for this least optimal case, the trailing foil is seeing the opposite. When it's going up, the flow angle is pointing down, so that will decrease its angle of attack. When the foil is going down, as you can see here, the velocity is pointing up. That's the effective angle of attack is always minimal, and then the formation of leading edge vortex is suppressed, and then the force is getting small, diminished. I think using this way is more straightforward to show that. And then I think, yes, as Professor Hong just mentioned, Kenny was here a few years ago, and I guess he was showing some field testing about this project. I'm showing just one slide of that, and we did 2 phases of field testing. One is on a boat, the other is in the Cape Cod Canal, and you can see this image is the phase 2 is where we have large foils deployed in the Cape Cod Canal. And I just want to show some quick results. Basically, want to confirm that the flume efficiency and also the field efficiency, the flume efficiency are those dotted lines, and then the field results are those stars. And you can see that they have good alignment with respect to this optimal reduced frequency here, and considering all those frictions, the efficiency is really matching really well. Yeah, and here we have this electricity generator here to measure those generated power. Okay, so, and then the second part the second project of the first part, I would like to introduce the cyber-physical system for you, especially because it's very, very powerful and very relevant in those water tunnel or those wind tunnel experiments. So this project was also finished at Brown University with Professor Kenny Breuer, and I will briefly talk about the energy harvesting using the cyber-physical system. So before that, I would like to talk about those prescribed and flow-driven system. So in the previous example, which is the tandem foil, that's a prescribed system. That means I prescribe the sinusoidal motion, and then I measure the force, and then I can estimate the energy harvest efficiency. But that's kind of like one-way coupling, so I prescribe that and it gives results. But in reality, there were some, well, the real thing should be flow-driven, so you don't prescribe the motion, but the motion is driven by the flow. And then the fluid force together with the structural force will together determine the frequency, the motion parameters. And this is called like two-way coupling. But usually in reality experiment and also in those deployment, those flow-driven system is not easy to implement, especially if you want to explore multiple different parameters. For example, in this case, different damping, different stiffness, different mass. It is hard to do that. So, and then we use a cyber-physical system to do so. So the cyber-physical system basically it has two components. One is the physical part. So it has for example, it has a physical foil in the water flume, measuring the forces, and then can be controlled to go back and forth. And also it has a computational system that will take into those forces and then output some arbitrary complex structural dynamics. So I will give you a very quick example. So this is the cyber-physical system I designed at Brown. So this is only the heave component. Heave motion is controlled by cyber-physical system. And so this is the governing equation. So spring mass damper system in the computational, in the computer, or it's a cyber part. And then the fluid force, the physical part, fluid force, basically if you have fluid flow, and then, or if you give it a pulse, just like what I did, it's my hand pushing it, basically you give a momentum and it will move back forth. And then just like a spring mass damper, it would die down eventually like that. So here's how it works. Basically, the force, usually the fluid force will be measured in real time and then sent to the computer in real time. And then the computer will determine those acceleration, velocity, and the position output together with the structural force. For example, you have the fluid force coming in, and then the foil is also subject to those structural force, mass force, damping force, stiffness force. Together, it will determine a position output. This is a position loop, force feedback position loop. So because the sampling rate is really high, in this case, it's a few thousand samples per second compared to those low frequency water flume experiments. So the response is really high. That is really accurate, as you can see here, theory and the measured. But if you want to do it in the wind tunnel, which the frequency is much higher, we can always increase the sampling rate of the system so that it will work as a kind of real-time system, will react to those forces or impulses in real time, just like in this case. And then I will give you a very quick example about this, about energy harvesting. So in this case, the pitch motion, which is a rotation motion, is prescribed just to actuate the energy harvesting process. And the heave motion is flow-driven, in this case, using the cyber-physical system. And then I can change the mass, the stiffness, and the damping here, and then to explore whether we can get this maximum energy harvesting efficiency out. So here's the natural frequency determined by the stiffness and the mass and the frequency ratio between the natural frequency and the driving frequency, which is the prescribed frequency here. And then the damping coefficient, you will see that later, power coefficient. And then this is the result. Basically, we can see that there's a clearly defined peak in this color map, where you add the frequency ratio of 1 and the damping coefficient about 1.5. That means that in this subphysical system, we can still get this energy harvesting with this really high efficiency out for the system. This is a very quick example, but I would like to talk more about these other applications using the subphysical system, especially in this flow-induced vibration, because you can see a lot of those examples of flow-induced vibration. For example, those airplane wings, the fluttering. Also, the most famous one is the collapse of the Tacoma Narrow Bridge. This is a real bridge, and it's kind of like twisting like a noodle under some strong winds. Flow-induced vibration. Also, this is a cylinder. You can imagine that this is a power line, and then under a strong wind, especially there's a storm, and then the power line which is vibrate, and you can hear the sound. So this is a two-way coupling between those nonlinear aerodynamics force. I'd like to show this. It can be simplified as this kind of system, a pitching wing, or is elastically mounted pitching wing. Is a two-way coupling between those aerodynamic force and the spring mass damper system, and it could be good if you can control that and use it for energy harvesting, or it can be bad, especially for the structural failure. So this is the model, well, not the model, this is basically the setup. And so basically you have the flow coming, uniform flow, and then you have airfoil or wing in this flow. And the wing is fixed or mounted, elastically mounted by this spring mass damper system. And you can set, for example, you can set a spring to be really large, and at the very beginning, and it will be static, it will be not moving at all. So, and then you have two systems, the structural force and fluid force here. And so the governing equation is similar to the heaving part, and the Reynolds number in this case is 50,000, and this is a fixed parameter. And the damping coefficients are 0.13, so we normalize the damping using those fluid properties here. And the control parameter that we vary is the inertia, also the stiffness. And the stiffness here is actually the inverse of the Cauchy number. We'll be using that. This is the control or the variable that we can change. And then the output parameter is the amplitude of the wing and also the frequency of the oscillation. So let's look at some very quick, simple results. So the output is the amplitude and the frequency. Let's first look at the amplitude response at different inertia. So this is the low inertia, really low inertia compared to those fluid inertia. And so here's how it works. Basically, in this free stream flow, we mount the airfoil with zero angle of attack to the free stream. And to start with, we set the spring stiffness to be large so that there's no motion at all. And then when we decrease the stiffness, we can see that to some extent it starts to oscillate. This is a small amplitude oscillation, and then we further decrease the stiffness. As you can see here, and then the oscillation gets larger and larger. And then when we increase back the stiffness, we can see that the amplitude just follows the same path back to where it was. And this is called the supercritical bifurcation. Basically, there's very smooth amplitude transition, especially there's smooth going up, and there's no hysteresis. Now, when we change the inertia to much higher, 30 times higher in that case, the same experiment, zero angle of attack at the very beginning, and decrease the stiffness to some extent. We also see some small amplitude oscillation, and then suddenly it jumps to this large limit cycle oscillation. And then if we decrease the stiffness more, and then it gets larger and larger amplitude. And then if we increase back the stiffness, then it will not stop at this onset point. Instead, it will go much further back to here, and then suddenly stop here. And you can see this is the hysteresis part here. And the characteristics is that it has amplitude jump, and it has the heuristic stability here. So, and then what is those inertials in between? And then we look at those multiple inertials and then plot those curves. We can see that when we decrease the inertia here, the curves for here, those bifurcation curves move from left to right. This is how it moves. And then, especially in this case, we can see that for multiple different inertials, the onset point, where the amplitude jumps, is the same for all those different inertials. But the disappearing point is different. You can see here the different disappearing point. But if you use another scaling, which is the dimensionless velocity, this is the velocity, non-dimensional by the structural frequency or the natural frequency. And you can rearrange the terms to give the inertia over the stiffness. And in this case, the onset now is different for different inertias, but the disappearing point now is the same for all those high inertial case. And this is because that in this case, the inertia is taken into account in this case. And then we look at this frequency response. So previous was those amplitude response. The frequency response, we are plotting this natural frequency or structural frequency on the x-axis, and y is the pitching frequency here. And we can see that when the inertia is large, basically the pitching frequency is locked into those natural frequency. This solid line is one-on-one locking. It's very close. But for when the inertia is very small, as you can see here, and the pitching frequencies deviate a lot from the structural frequency. And it's its own time scale, as you can see. And then we look at the forces and see what's going on in the force. We can see that in this high inertia case, the competing or dominating force components are the inertial force and the stiffness force. And together, they will determine the frequency. And we call this structural mode. And then when we're looking at those low inertia case, we can see that the dominating components are the stiffness force and the fluid force, which is we call the hydrodynamic mode, because now it's competing between the hydrodynamic force and the stiffness force. And then the question is, why is it doing this, right? And then we look at this problem from this energy balance or energy approach. So basically, the energy transfer in this system is the kinetic energy transfer into the system, the pitching system. And then mathematically, you can see that if you just multiply by the velocity on both sides, and then these two terms will cancel because they're out of phase when you're doing this time integral over a cycle. And the only remaining term is those fluid force and the damping force. These two forces will be, for example, the fluid force will be injecting energy into the system, and damping term will be consuming this energy, just like an electricity generator. That's the damping. Or you go to the gym, you're pulling this. It's a damping. You have this mechanical energy transfer into the damping. And then when it is at this steady state oscillating without any change of the amplitude and the frequency, and it is reaching a steady state, and the energy budget will be the same. That means the fluid force, the fluid energy will be damped out exactly by the damper. So that's why the sum will be 0 here. So and then basically here we're trying to look at the energy response of a pitching wing. Basically, we prescribe the system and then export a range of amplitudes and frequencies in this equation, and then estimate those energies. So this is the energy response of the pitching wing. So with various amplitude, various frequency, and you can see that in some combinations this is positive. That means That means that there was energy injected into the system, and then there's some blue areas. That means it's losing energy to the fluid, and there's in between. There's like power is 0. There's basically no energy input, no energy output in that. And then this is injected, which is the blue. And if you just superimpose those damped case, in this case, you will be subtract more because it will be damped out, and then the boundary for the Cp equals 0 will be going further in here, and then we just need to reconfigure this a little bit. We just rearrange the same figure, but now the frequency is going down so that it matches the previous diagram of the instability. So in this case, we can see that there are basically 2 branches of Cp equals 0, the top branch and the bottom branch. And then we can see that in this case, when the inertia is high, the instability branch falls on the top line here. And basically, here's some explanation of that. So just assume that you have the system is running at this point, and then you have this red. That means there is more energy coming into the system, and the system will grow. Grow by what? Either by the frequencies increasing or by the amplitudes increasing. That's how the systems grow. Because this case, the frequency is locked into the structural by the natural frequency. What you can only do is to increase the amplitude. So if you have a case here, if there's a point, if you have a state here, means here blue means now the system is losing energy. That means the oscillation will die down either by reducing the frequency or reducing the amplitude. But the frequency is locked into the system. You cannot change the frequency. What you can only do is to change the amplitude, to drop the amplitude, and then you will eventually reach here. The same way when it is at the red area. So if you have more energy, what you can only do here in the system is to increase the amplitude so that it reaches the steady state. That's why you have those steady state on the upper branch here. Yeah. And then the same way if you in here, you will, instead of going to this branch, you will going down because now you have those blue, that means it's going down, and it will go down to the static state. The same way for those the lower branch. Actually, the lower branch is the same way as in this the previous one. In this case, the lower branch is corresponding to the supercritical one, where the frequency is not locked in. So that's how you do that. For example, if you have a case, for example, this case, and you have the energy which is lower, and then, but you cannot increase the amplitude, or you can increase the amplitude, but at the same time you can increase the frequency. So you can decrease the frequency. In this way, the frequency is decreasing. You can decrease the energy by decreasing the frequency, and eventually it will fall at this point. Similarly, if you have more energy, so the system will grow by increasing the frequency. And then that's why it's traveling left to right, and eventually it will stay in this stable line curve, lower branch over here. Yeah, this is a very quick explanation of why we have these 2 branches, 2 bifurcation branches here. Yeah, and this is the criteria for those instability. Basically, it's the gradient. So for the structural mode, the power gradient with respect to the amplitude needs to be negative. That means it has to go towards the amplitude decreasing point direction. Yeah. Yeah, so this is a quick summary of the part 1, and then I will move to part 2. Briefly, I will briefly talk about 3 quick projects about those animal locomotion. So the first one is about those kobupa swimming. marine organism, copepod swimming, individual and swarm migration. So before that, I would like to introduce a term called diel vertical migration. So it's a daily synchronized animal migration between the surface layer of water and the deeper layer of water, basically exchange. So those animals will move in a daily manner up and down. And so it can then potentially bring some of those oxygen-rich water from the top to the bottom, and then bring those nutrients from the bottom to the top. And then to understand further this question, so we use the copepod to see its potential effects in the lab experiment. So first, we're looking at this individual copepod swimming. We use this in-house micro PIV here. This is a particle shadow velocimetry here, and we use those algae as the tracer particles here. And then this is just very quick example showing that the copepod is moving up, and then the induced flow field is downward. In this case, the induced flow field now is also downward if you're looking at the side here. And then the question is, this is the individual scale. What about the swarm scale? Because eventually we're going to look at those swarm scale migration and their impact on the fluid mixing or transport. And here is the experiment about a swarm migration of copepods. And then here we use this setup basically is those copepods are phototactic, and we first concentrate at the bottom and then turn on the laser on the top and turn off the laser on the bottom. So the copepods will then migrate towards the top. And then the same way you can create a downward migration as well. So, okay, so here is the result. And this is upward migrating copepods. And you can see that they are generating a downward flow. And on the right is the downward migrating copepods. And they are also generating a downward flow, which is different from what people was thinking. So people usually think, okay, for the downward migration, they would generate a upward jet because you need to push the fluid backward to get this forward momentum. But it turns out, no, the opposite. And this could have some potential impact on this fluid transport. But before we talk about that, we want to introduce another very interesting observation, which is the also downward migration of copepods. And then it changed the color code. Basically, the green is going down, green is the velocity going down, and the red is going up. You can see at the very beginning is green, and then it transitioned to red, which is the induced flow field is upward. And then gradually it transitioned back to green again. This is kind of like flow reversal. Let's play that again. So this is a really interesting part. We have not yet figured out why it is doing so, but we're trying different ways. Yep. The flow is using other. It's very small tracer particles, PIV particles. Yeah, much smaller. Yeah. So, yeah. So very interesting part. Observation, still trying to understand this, why it's doing so. So, and then coming back to this potential impact. So basically what we're doing is a lab scale experiment, and we're trying to use those flow fields, flow characteristics, and then to inform some continuous swimmer model, and then use this information to fit in a even larger global ocean biogeochemistry model that our collaborators were working on. Yeah, this is basically what we're doing, and is rolled in this project. And then I would like to jump to those jellyfish swimming, and then we are doing those live animal PIV experiment, and then the issue is that the animals do not like those commercial synthetic particles when in this PIV, they might just intake those particles as food, but they cannot digest it. They digest those particles. So that could be an issue for the animal's health. So we're trying to find some biodegradable particles for this live animal experiment. So yes, basically we identify a few, for example, starch, corn starch, potato starch, and arable starch. We explore multiple of that. And we do some microscopic images and look at the distribution and the sizes. And then we test this with those brine shrimp, very small creature. They can basically take this as food. If those are commercial particles, they can just more function after that. And the left is the commercial one, the right is the biodegradable one. You have very comparable flow fields, very qualitative measurement here. And then another part is the jellyfish swimming. So in this case, I would like to show some quick results about the jellyfish swimming. So we are able to track the jellyfish, their position, the morphology basically in real time. And then for example, this purple dot is basically this is the time history of that. And then using this, you can then calculate the swimming speed of the jellyfish here. You can also use the yellow and the cyan dots to look at the contraction of the jellyfish bell. You can see this contraction, the relaxation, and then just wait for some time, and then another contraction, another relaxation, another one. So yeah, and then we analyze the jellyfish swimming speed and then try to find some scaling for that. This is a scaling used in the fish swimming, this flapping fin fish swimming. And this is given as a Reynolds summer to the swim number to 4/3. And the swim number is defined as the beating frequency and the amplitude and the diameter and the viscosity here. And then if we use the same scaling for the jellyfish swimming speed, for different sizes, small jellyfish, large jellyfish, and different dots basically are for different repetitions. We just repeat this experiment for multiple times, and then they might have different, the same jellyfish might perform and behave different swimming speed at different trials. That's why we take as many possible trials as possible. And then we plot it here. You can see that those jellyfish swimming actually follow this pattern really well. And then jellyfish can also be used as a robot, basically. And this is the biohybrid jellyfish robot. That means hybrid means the jellyfish is still alive, and then we're embedding these microcontrollers to control their motion. So why jellyfish? Because jellyfish is very simple, and then their neural system can be actuated by those simple electric pulses, just 4 volts. And then if you supply these electric pulses, and the jellyfish will respond and contract. And then through this, you can basically control the contraction of the jellyfish when it is still alive, and then move forward, basically, as you can see in this case. And this is the field view experiment you can see in this case, and this is the jellyfish. And this is what I will trying to replicate it in my lab as well, and move forward beyond this. And especially the challenge in this project is now you can perform and go straight, but the turning part is difficult, so we cannot go turn. We cannot make it turn in this way. So yeah, the last part I'd like to talk about is the next step. Basically, we'll continue with those energy harvesting flapping foil in a very unsteady flow conditions. And at the same time, we'd like to look at those tandem wings for highly efficient and maneuverable proportions. And then I would like to continue with the zooplankton migration in those lakes and utilizing those available devices and resources in the Large Lake Observatory. And then with that, I would like to thank these people from various institutions, from Brown University of Boulder, and my collaborators, also new collaborators from the UMD Duluth, And thank you for your attention. I'd like to take any questions.
Thank you very much. Very diverse range of applications. Let's say if there are any questions from the audience. Judy. Yeah, Chris. Judy, go ahead.
For your protocol in a screen defined tank, I feel like the flow entirely is 3D and the capture is using 2D. And if you are using TIV, I feel like there are thermal effects can drive some flow and how do you carry that?
Yeah, that's a good question. So this first like about 2D or 3D. So this is a let's say it's a laser sheet. So the flow or the generated flow is mainly 2D because we are generating a laser sheet, and the animals they are swimming in this within this 2D laser sheet. And also we did additional experiment with two lasers. One is from here, laser sheet, and then we're looking at the flow field from the side so that we can see whether there's like 3D flows on the side or not. We didn't find those 3D flows in those 2D laser sheet induced flows. And then the second question is about those thermal effects. Yes, there could be some, but the good thing is that we are doing the laser sheet. That means the thermal effects being minimal because it's not like laser point. In that case, the concentrated heat will be really strong. And the laser sheet, the thermal effect is very small compared to those, for example, ambient, those, let's say if the tank, let's say in this way, if the tank is open to the air and then there's some ambient induced convection as well. But in this case, the thermal convection is very small compared to those flow induced by the animals. Yeah. Yeah, that's a good question. Eventually, yes, there will be, and that's why we use a really large tank, and as large as possible, so that those upward flow will be kind of like redistributed uniformly by the size of the tank. Yeah, that's a good point. Yeah.
With the flapping foil,
Yep.
it seems like most of its regime, you had very large angles of attack. With the foil, so most of its regime was a separated flow.
Yep.
Most of the time, people try to operate foils to avoid separation to maximize lift.
Mm-hmm.
Why is this not moving like that?
So yeah, that's a good point. In those aerodynamics, if it's like airfoil, static, over there, it's not dynamic.
Water foil.
Yeah, well, for either way, so if it's static, it's not moving, and then we will use those, let's say, attached flow and no separation. That would be the ideal. But in this case, it's like dynamic. That means it's going up and down. In this dynamic case, the leading edge vortex actually is good. It's good. It's good for this lift force generation. Yeah.
You get less lift.
You get more.
Or if you used a lower angle of attack and made sure it was just non-separated.
Yes, you will get less lift force compared to this large angle. And
You get a lot of drag, but drag doesn't matter.
exactly. That's a good point. Yes, it got a lot of drag, but doesn't matter because it does not need to move forward. Yeah.
Any other questions?
Yeah, yeah.
All right, yeah, let me just add a couple questions. The first one is related to your energy harvesting system. You showed multiple different things related to energy harvesting, all right?
Yep.
I understand the first one is more passive, that you go into the cyber physical system that's some actuation to optimize the energy harvesting. Is that the kind of logic thinking behind this? Eventually you want to make this to be a more smarter energy harvesting system.
Yeah. So after I talk about tandem thing, and then I was talking about this passive one. Yeah, the motivation is that eventually the system will go passive, and then we need to understand how it performs in a passive system. And also, the field testing is also within a passive system. And let's make this point. In the field testing, the electricity generator actually is very similar to the damper. It does not have a spring, but it has a damper. You can tune the damping in the electricity generator. That's very similar to the cyber-physical system. And the good thing is that you can have some structural thing in the field testing. Like it will still be flow-induced vibration with damping only. Yeah. Yeah.
So I'm just, I think the short summary of my question is whether this cyber-physical system is connected to the first part of your talk. Is it connected or now it's separate?
It is connected. So the first part, which is
this energy harvesting the heat motion tendon system.
okay, no, those are not. Those are kind of different. Different. The tendon one basically is to find the sweet spot to deploy the second foil. The cyber-physical system basically is to figure out how the system will perform in a passive controlled manner. Yeah, they serve different purposes. Yeah.
So a related question, if you want to deploy this in large scale, like in the wind farm, you have different wind turbines. You understand the layout optimization is an important question for wind farm development, right? Wind farm designs. I'm wondering, is there any similar questions, in your wave harvesting system, where you show just the Rhino 2 tendon system, but for optimization problem, you are giving out a certain surface ocean area, right? How do you maximize energy extraction from the area? So there are several factors play the role in the optimization. It's not just the efficiency of
So the total,
so
the system.
Have you thought about stuff like that, or has anybody done work?
Yes, I also thought about that, and I guess there are people working on those. I guess the first thing is the configuration. So there are configuration. The one I'm looking at is the most simple, straightforward one. Is one behind another, and there's another configuration. This is a leading one, trailing one. The one is offset for some distance, and this one, and the offset one usually can benefit a lot from the leading one. And then, so if you think in this way, there's one offset and there's another one in the trailing. So for the third one, it is also offset compared to the second one. So that is actually I guess it's an ideal configuration for those energy harvesting. Now people have looked at those performance of the trailing foil when it is at an offset position. Yeah, and then you can.
But they haven't looked at this.
No.
Bond scale.
No.
Right? For example, multiple different tendon systems together. How do you lay out a spacing between them, or?
Yeah, I don't think people have looked at that because from the experiment point of view, it will be hard to have multiple foil set up. But I guess in the field, it might be. Well, I guess simulation might be a better solution to this. Yeah.
All right. All right. Sounds good. Any other questions? All right. No other questions. Thanks, Peter.
Thank you.